Hello and welcome to a new lesson from Easy Chemistry. This is Mr. Kusai, and today we're going to continue what we started last video. In a previous video, we were talking about Hess Law and the heat of formation. Today, our objective is to solve more problems about Hess Law and the enthalpy of formation. We're going to use this table in order to find some enthalpy of formation for some substances. In the previous video, we stopped at this problem, and I asked you to try to do it by yourselves. Problem 1, calculate the standard enthalpy of formation of acetylene C2H2 from its elements. And you are giving three equations about the steps for the enthalpy changes for the desired reaction. So basically, we're going to call this reaction the desired reaction, that we need to find delta H for it, delta H. In this case, they are asking for the enthalpy of formation because it's from its elements. So I'm going to call it delta HF standard. How to solve these problems? We always need to look at the desired reaction and then at the products and at the reactants. How many moles on each? So in equation A, you will find that graphite is at the reactants. And also we need it at the reactants in the desired reaction. So we're going to rearrange reaction A, and we're going to give it A star. Here, I have it only 1 mole, but I needed 2 moles. So what I'm going to do is to multiply all this equation by 2 in order to get 2 moles. Don't forget, when you multiply an equation by 2, you need to multiply delta H for the reaction also by the same number. So I'm going to rewrite this equation A. It's going to be C graphite plus O2, of course, 2 here, yields to 2 carbon dioxide. So this is the first reaction is ready. So 2, 2, and 2. Now, the new delta H for this reaction, it equals to 2 multiplied by negative 393.5 kilojoule per mole. For the second reaction, also we need to check what do we have. We have H2O, but we don't have any H2O in the desired reaction. So never mind the second reaction. But we have H2 in the reactants, and also we have it in the reactants. So I'm going to rewrite reaction B, and without doing anything to it, because 1 mole of H2, and I have 1 mole of H2 in the reactants, So it's going to be H2 plus half O2 yields to H2O. Delta H is going to be for this reaction the same, which is negative 285.8. In the third reaction, reaction C, I need C2H2 at the product, and I need only 1 mole. But here I have it in the reactant, and I have it 2 moles. So I need to multiply this one by negative half. Why negative half? Negative because we're going to flip this reaction, and half because I need only 1 mole, but we have 2 moles. So I'm going to rewrite reaction C, and it's going to be products divided by 2 yields to the reactants divided by 2. So it's going to be 2 carbon dioxide plus 1 H2O yields to 1 C2H2 plus 5 over 2 O2. Now, delta H for this reaction, the new delta H, is going to equal this number divided by 2. So negative 2598.8 over 2. Now, I need to add these three reactions in order to find the delta H for the desired reaction. So I'm going to add these three reactions. Don't forget the product with the product, you add them. The reactant with the reactant, you add them. But the product with the reactant, you cancel them or you minus them. So I have two carbons and I don't have any other carbon. I have two oxygens plus half oxygen, that is 5 over 2 oxygen. 5 over 2 oxygen here and 5 over 2 oxygen, so these will cancel each other. So no more oxygens in this reaction. I have H2 and I don't have any H2, so I'm going to write it as it is. I have 2 CO2 and I have 2 CO2 in the product, so I'm going to cancel this and this. I have one H2O and I have one H2O, so I'm going to cancel it. I only have C2H2 in the product, so I'm going to write it as it is. So the final reaction will be 2 carbon plus hydrogen, H2, yields to C2H2. And to double check, we need to check, is it the desired reaction or not? We find it's the same. 2C plus H2 yields to C2H2. So our work was correct. Now, because we added A, B, C stars, I'm going to add also delta H for the reaction, which equals to, by the calculator, you're going to do 2 multiplied by 3, 9, 3.5. Here we multiply it by also by negative half, so the sign will change into positive. Now, I want you guys also to double check with me. And the final answer should be 226.6 kilojoules per mole. This is how we solve this problem. So basically what we did is only to arrange those equations, the given equations, in order to find the desired reaction. And when you flip the reaction, you need to multiply it by negative. When you multiply the reaction by a number, you need to multiply it also, or you need to multiply delta H for it also by the same number. And then you add those steps to find the desired reaction, and therefore you find the delta H for the desired reaction. Problem number 2. The thermite reaction involves aluminum and iron 3 oxide, and this is the desired reaction which is given. This reaction is highly exothermic, and the liquid iron formed is used to weld metals. Calculate the heat released per gram. We all know that delta H, whenever we talk about delta H, it's kilojoule or joule per mole. In this case, they need it for per gram, so they make it a little bit more complicated. Of Al reacted with the Fe2O3. And you are given the standard enthalpies of formation. You are not given now equations, step equations like A, B, and C in this problem. So you are given directly, you are giving the standard enthalpy of formations. And also you are giving the molar mass of Al, aluminum. And they need it for the aluminum. How to solve this problem? We have this equation, which is delta H for the reaction. It equals to the sum of all delta H's of the formation of the product minus the sum of delta H formation of the reactants. In this case, we're going to use this equation. So here are the products. So we need delta H for the reaction equals to, for the products now, we have Al2O3, and for Al2O3 is negative 1669.8. And we have it 1 mole, so I don't need to multiply it by anything. So it's going to be negative 1669.8 plus the second product is Fe. Some of the students will ask, okay, Fe is a pure element. Why is it? Why the delta H formation for Fe is not 0? Well, because it's not at its standard state. We all know that the iron at standard state or standard condition is solid, but here it's liquid. That's why delta HF is not 0, which equals to 12.40 kilojoule per mole. So plus 12.40 kilojoule per mole, and these are for the products, minus for the reactants. We have 2Al, but it's solid, it's element at its standard state, so it's going to be 2 multiplied by 0, plus we have it for Fe2O3, which is negative 825.5, so plus negative 825.5 kilojoule per mole. We will do the math now, which equals to and that should be negative 831.9 kilojoule. But kilojoule per how many moles of Al? We have 2Al here. So it's going to be negative 831.8 kilojoule per 2 moles of Al. And why are we writing per Al? This is the delta H. If they are asking you here in this reaction, if they are asking you what is delta H for the reaction, that's it. It's finished. It equals to 800 negative 831.9 kilojoule per mole. See? If they are asking you what is delta H for this reaction. But in this question, they are asking you to calculate the delta H released per gram of Al. That's why we write this delta H is for 2 moles of Al. And you are given the molar mass, which is MW of Al. Now, we need to convert these moles into grams of Al. Don't forget that the number of moles equals to mass over molar mass. So we're going to do the unit cancellation method, which is negative 831.9 kilojoule per 2 moles Al. I need to cancel mole of Al, and I need to find the grams of Al in the denominator. So I'm going to write here 1 mole of Al divided by the molar mass of Al is 26.98, so 26.98 grams of Al. So unit cancellation, mole of Al, mole of Al, leaving the unit only ground. So doing the math now, which equals to 15 negative 15.42 kilojoule per gram Al. It's very simple, but they connected two concepts together. These kind of problems, it comes in the AP exams as well as the MSAT exams. So we need to make sure about those tricks. All right. Problem number 3, use the following calorimetrically determined enthalpy changes to predict the standard enthalpy change for the reaction for the ethane with chlorine gas. And you have this reaction, which is also the desired reaction that we need to calculate delta H for it. We have 3 reactions. I'm going to give it A, B, and C. If you see, the first reactant is C2H4, and we have it in reaction letter B. So we have it 1 mole, we need it 1 mole, so I'm going to rearrange it. B star is going to be C2H4 plus HCl yields to C2H5 Cl, and delta H for this reaction is not changed, which equals to negative 65 kilojoule. I have here, for example, we need HCl, which is 1 mole, but I have HCl 2 moles in this reaction. So I'm going to rewrite A to make it 1 mole. So it's going to be, well, actually, in this case, before we do anything, before we rearrange, we need to take a look at those. We have 2 HCl here, and we have 1 HCl here, and we have C2H4 here. So I don't need to do anything. If you add these two reactions, one of the HCl will remove HCl, as you can see. So the only trick now is reaction C. So I'm going to rearrange reaction C because I need C2H3Cl in the products, but I have it in the reactants, 1 mole and 1 mole. So I'm going to multiply this reaction by -1. If you multiply this reaction by -1, it's going to be C2H5Cl yields to C2H3Cl plus H2O, and delta H for this reaction equals to positive 140 kilojoule. Now let's add A, B to C star. We have 2 HCl and we have HCl, so here we have only 1 HCl left. We have also, sorry, here is H2 only, not H2O. We have H2, 1 mole, and H2, 1 mole, they cancel each other. We have also C2H4, it will go down, Cl2 will go down, and C2H5Cl, C2H5Cl, they cancel each other. Therefore, the final reaction will be the desired reaction. Let's write it again. It's going to be C2H4 plus Cl2 yields to C2H3Cl. Cl plus HCl. So all what we need to do is to add reaction A, reaction B, and reaction C star. That means delta H for this reaction equals to negative 110 kilojoule. This is how we use Hess law in order to solve some problem about the enthalpies. Last problem, use standard enthalpies of formation to calculate the enthalpy change of this reaction. We have the desired reaction, delta H is unknown for the reaction, and we have the heat of enthalpies. It's very simple, delta H Rxn standard, it equals to the sum of delta H's formation for the products minus delta H, the sum of delta H formation of the reactants. The product is 4H3PO4, so I need to multiply it by 4 minus I need to multiply H2O by 6 because I have 6 moles, and this one multiplied by 1. So it's going to be 4 multiplied by negative 1279 minus 6 multiplied by negative 242 minus 2940, and it equals to negative 724 kilojoule. I want you guys to double check this problem, go solve it by yourself, and find the final answer. I hope you guys learned something new. Please keep tuned because next lesson is going to be about the enthalpy of combustion, and we're going to finalize all the problems about this section. Have a good day. Bye-bye.